In this lecture, uh, we will talk about the index notation for the vector calculus. As you know, index notation, also commonly known as the subscript notation or tensor notation, is extremely useful tool for performing vector algebra. When we consider the coordinate Cartesian coordinate system in figure 1, instead of using the typical axis labels x, y, z, we use in x1, x2, and x2. So we can represent all these coordinates x, y, z like xi. I is represent 1, 2, 3 for 3 space. And basically for the 3 space, the corresponding unit-based vectors are that e1 in e2 in e3, and we can represent similar to x coordinates and unit bases like ei is again here 1, 2, 3, and 3 space. So the basic vectors e1, e2, e3 have the following properties, and e1 dot product e1, e2, e2, e3, e3 gives the 1. The others otherwise it gives the 0. E1 product e2 is 0, e1, and because they are perpendicular each other, so we call this orthogonal each other and give the 0. And these are, you see, the e1 in e2, e3, the basis vectors is unit 1, the others a1 and a2, a3 is represent the xyz axis. If we continue, now we know the Kronecker delta symbol is Rg, and Rg has the following, this symbol is the following properties. If I and G is not equal each other, is give 0. If I and J is equal to each other, is give 1. In here, I and G is the 1, 2, 3 in the 3 space. So using the equation 3, equation 1, and equation 2, maybe reading the index notation is following. That product of the bases in here, we see basis vectors in here is that product of the unit vector ei and eg is give this, I don't know how to call this, okay, this symbol in Ig. So it's go Ig in here 1, 2, 3. In a standard vector notation, let's say if we have the vector A is the arrow in above it, so we understand from this definition is we are dealing with the vector, and we can represent the vector like this: ix is to represent the x-axis and unit vector I, plus iy y-axis, and g unit again here basis vectors. Then plus iz is k is the in z direction, z axis is the k unit basis. Using the index notation, we can represent this again the vectors like this: a1 and e1 plus a2, e2 are plus e3, a3, e3. We just exchange. This is the by a1, this is a2, this is a3, and this is I is e1, j is the e2 and e3. Then we can represent all this vector by this summation like here, and here ie and ai and I here start from the 1 is equal to 3. So this is the summation is repeated in here, and can repeat the I like a 1, 2, 3, for example. And so, but typically we can write these terms inside of summation just like this in here, because in general we deal with the 3 space. We know how many axes we have, how many direction or dimension, so we can repeat 1, 2, 3 mostly. This repeated index notation is known as the Einstein convention. Any repeated index is called dummy index. Since a repeated index implies a summation over all possible values of index, one can always relabel and the dummy index like this: a vector, and you can write ai, ei, ag, eg, and ak, and ek, so on. So the open form is n of this is given like this interspace. So another topic is we talk about is the scalar product in index notation. Okay. Now show how to express the scalar products, also known as the inner product or dot product, using the index notation. Consider the vectors and a and b, which can be expressed using the index notation. Vector a is represented like this in open and closed form like this, and vector b in similar case we can represent like this. And the dot product or inner product of between vectors and a and b, the vector a dot product vector b, and you can write all these vectors inside of the summation form: actual I, e, ai, ei, and b, g, and eg. And we can using the commutative property, we can bring this form a ai and bj, and in our dot product between the bases and ei dot product ej. Then what was the dot product of ei and ej was like this form Kronecker delta. So it's give this result from the equation 3. So summing over all the values of I and g, we just get this form. Okay, just put a1, b1, and 1, 1, a1, b2, 1, 2. If we write all the possible combination, at the end we get this form, all these 9 terms here, and some terms in here is if I and g is equal to each other is give 1. If I and g not equal to 1, we know from the above as give the 0, this 0, this 1, 0, 0, 1, 0, 1, 0, 0, 0, 1. We just have the final this 3, and these values give 1, this 1, this 1, and then as a result it left a1 b1 plus a2 b2 plus a3 b3 is give us the dot product between the vectors in a b. And so we can write the dot product between a and b in this form, closed form, and or this form in any case. So Kronecker example data reduction. Reduce this reduction. How can we reduce this? Rg, gk, ki. So remove the ej by setting the j equal to I everywhere. So if the e, I, and g is equal each other, this is gonna be, for example, if we set the j as a I, then it's gonna be 1 1, and it's give the result just 1. Then it's reduced to this following form. In here the j is gonna be exchanged with the I, then it's gonna be ik, and it's gonna be here the ki. In the next step, if we set the k equal to I, then it's gonna give is the if the k is equal to I, it's gonna give 1. Here k is equal to I is gonna be left this, then this is gonna give the result of the 3, because if we repeat this 1 1, 2 2, and 3 3, because they are gonna same, and numbers, then it's going to give the result of the 3 as we seen here. And note also from this example, this 2 is give the result of this. Okay, in the next topic is the cross product of index notation. When we consider again the Cartesian coordinates in the figure 1, using the conventional right-hand rule for the cross products, we have like a E1 cross product E1, E2 cross product E2, E3 cross product E3 is equal to 0. If you remember from the right-hand rule, and same cross product of the same bases is equal to 0. But the cross product of the E1 and E2 is given the E3, and the cross product of the E2, E1 is given the minus E3. By using the right hand, it's gonna give the finger your the other direction. That's why it's minus. And cross product of E2 between the E2 and E3 is give the E1, E3, E1 is give the E2. The otherwise is give the minus values. So to write the expression in the equation 12 using index notation, we must introduce the symbol it's a IGK, which is common known as the tensor and alternating unit tensor or permutation symbol. In we can call in 3 name. This has the following properties: is if the IJK is even cyclic permutation, then it's a 1 2 3 2 3 1 3 1 2 is give this permutation, this cycle order is give the 1 as a result. If this is odd, then 2 1 3 3 2 1 and 1 3 2 is give the minus 1. Otherwise, if it's a 1 1 1 and 1 1 2 and 3 1 3 is give the 0. These are the 3 important properties of this permutation concept. So hence we may write expression 12 in here. We can write expression 12 like this. Now cross product between the E1 and E2 is equal to eta 1 2 3 E3, because here we obtain E3 since E1 2 3 is equal to 1, because this is 1, this is 1, this is 1, this is minus 1, this is minus 1, this is minus 1. Then we can rewrite everything in 12 in this form here. Now we may write a single generalized expression for all the terms. Then cross product EI and between the EJ is give the result at a IJK and EK. This is the general form of all these expressions. Here we can write in this dummy index case the dummy index here. Then, for example, cross product between E1 and E2 is give at a 1 to K EK. Then we can write like this, and we can, this is the closed form, and we can open this, and because K is repeated, and we can put instead of K is 1 2 3, and we can express like this, and from that this give us this 0, this is 0, and this gives us just 1, and that's why we obtain the E3. Okay. Also another properties is the eta IJK is equal to minus eta JIK, and equal is gonna be equal is the eta KJI. These are 3 is equal each other. So switching into subscript, reverse the sign of the permutation symbol like this asymmetric also. These are equal each other. And cyclic permutation of the subscripts do not change the sign of eta ijk. So let's consider the cross product of two vectors, and the vectors n a and b. We can present the vector a by this form. We can present the vector b by this form because these are two different vectors. We can dummy index I, this has the dummy index j, and cross product between a and b is gonna give this form. Then cross product is gonna be like this, I AI and BJ, and cross product between the EI and the EJ. Then the cross product between the EI and EJ is going to be expressed in the above. We see that like this. And last, we write the cross product between A and B like this, in this form. Okay. So the following is very important identity involving the product of two permutation symbols. If a product get the product of the two permutation symbols like this, all 6 different dummy indexes I, j, k, and lmn, we get this form. From here, the proof of this identity follows. It's given here. Then we obtain from here this part, it then is given that, or finally we get that part. So the product of these two permutation symbols give the result of this. These are important results. Later we are going to use in the problem solution. So, example, the vector identity proof. Let's say we have that one, A cross product B cross product C, and results cross product A. Let's say equal to A dot product C multiplied by B minus A dot product B multiplied by C. So the left hand side and the right hand side should be equal in here each other. And let's start with the left hand side. So we write the vector A. The vector is here, AI and EI. Cross product, we write cross product of between vector B and C. The cross product vector B and C should be that form because we get this result from here. We see this result between the cross product between two vectors. So we get this result and just we insert here. Then what we left, and we write everything is here, and we should get some cross product between EI and the EL. We know what is the result of the between two bases, cross product of two bases. Then these are same, you see. Then we get this as a cross product of that. Okay, we continue. And we take this here by changing the order JKL, and in here ILH we just change like this. Then we get product of two permutation symbols. The product of this permutation symbols give this result. We should remember from here like this. When we switch this result, then we obtain these two terms and multiply by these terms and these terms, then minus multiplication of these terms give that. Then by giving the values of this gonna give 1, this is gonna give 1. Finally we left AI and BJ, JCI, because we exchange between the K and the I. Then we have that, and we have the 1 here, and EJ, and we change the we made this J and the H equal each other. We did the same thing for here. Finally, we have that form This is the AI and CI, BJ and EJ. Then the right side. Then this is the dot product or inner product of the between the vectors of AC and multiply by B vector B. And this right hand side here, this represent the dot product or inner product between the vectors and AB, and it's the right other one is the represent the vector C. So you see left hand side is the same as at the right hand side. That's why it's the right equal each other. The another one, the scalar triple product, cross product between B and C, dot product, then result of this cross product and A. The right side, cross product between A and B and dot product C, cross product C and A, dot product B. Okay, we just take the left here and we write the vector A in this form. Then we write the cross product between B and C. We show how we wrote like this in the above. Then we can get dot product between EI and the EM. Then we obtain this result here. Then we exchange this result is M. Okay, and we just move to here. And what is this? This is the result of the this form B cross product C and result of this dot product of A. From our permutations rule, let's follow that here, and what we did, we bring the K, Rj and Jk and Bj and Ai, because we move the end and we obtain this, then we obtain that one. That's why both of them is the right one. Okay, basically this is the what we did in this lecture. We talk about the index notation for vector calculus and Kronecker delta, some basic rules and scalar product in index notation, inner product dot product or. Then we give some examples, cross product of index notations and the permutation symbol, the rules of permutation symbols, then basic results and some examples of these permutations symbols. So see you in the next video.